All right, so I'm going to be talking about this tool I like to use. It's called the COQ programming language, and specifically what you can do with it is use it to automate the correctness, like checking correctness of your proofs. So first we're going to go through a little bit of background, and then we're going to work through some examples to see how we can use this tool to formalize proof. So what is proof? So proof is, the thing that you learn to do in a course like Math 135 or 145, whichever version you're taking, and something that you'll use for the rest of your computer science or math degree or anytime you use math courses. So all the time in proof, we're given a theorem, and the theorem has some premises and makes a claim about a conclusion. And when you go about proving a theorem, you start off with the various premises, and you want to always derive the conclusion. And we're taught in Math 135 various tactics that we could use to accomplish this. So, the tactic that we start with might be, taking the premises and manipulating them somehow to construct the conclusion of the theorem. More advanced tactics could be something like doing case analysis. Then you also learn in Math 135 about, doing induction on an element in the premises to reach the conclusion, or tactics like the contrapositive. But all in all, like that in and of itself, this is what informal proof is. So it's kind of an art. The level of detail you'll go into is going to depend on the audience that you're communicating with. So the level of detail for a proof in Math 135 might be very different from some fourth-year math course. But the goal of an informal proof is always just to convince the audience, whoever that audience may be. And so this has some drawbacks, right? So even in a course like Math 135, you might be doing your proof and you might think, okay, well, this is very simple and my argument makes sense. But then the TA returns it to you and it turns out you've made a bunch of mistakes and you don't really understand why. And it might take a long time for the TA to mark your assignment. And it might also, be difficult to communicate with them or understand where exactly you were wrong when constructing your argument. And it's not interactive, to write a proof on a piece of paper. And so one way that we can kind of deal with all of that is to use a formalized proof framework. And so what is that? You can think of it as a programming language. And just like writing a program in a programming language, when you write a proof in a proof theorem language, you're basically converting your informal proof, which is like the algorithm of getting from the premise to the conclusion, to a program. So this is interactive. You can get instant feedback. And most importantly, the language itself provides a guarantee of correctness in the way that the theorem prover is constructed. So within this proof framework that I'm going to teach you about, or teach you how to use, it's going to be impossible to prove something that is false. And this is very useful, both for your assignments and for any kind of mathematical reasoning that you might want to do outside of that. So before I can really start to illustrate what I'm talking about with my examples, we're going to need to prove a few things. Or sorry, not prove. We're going to need to define a few things. So the first thing is going to be this piano notation for natural numbers. So we're going to define natural numbers inductively. We're going to define them as either being 0 or the successor of some other natural number. So every natural number that we can construct has to be constructed using one of these two constructors. So 0 is just going to be constructed using the 0 constructor. 1 is going to be constructed using the S constructor, which stands for successor, applied to 0. Can anyone think of what the number 4 would look like in this piano notation? I guess I can't see the chat anymore. Let me take a look in the chat. Yeah, that's right. Anubam and Raymond, sorry if I mispronounced your names. It's S of S of S of 0. So it's kind of, it looks like a piano as well. And the next thing that we're going to need to understand is how to define a function on this kind of inductive concept of addition. So the way we're going to do it now is we're going to define the function plus as a fixed point function that takes in two numbers, x and y, and returns another natural number. And the way that the body of the function is going to look is we're going to match x with the constructor that was used to build x. So if we match with the 0 constructor, we can just return the value y. 0 plus y is going to equal y. If we match x with the successor constructor, that means x is the successor of some other natural number x prime. So if that's the case, then we need to return the successor of the sum of the smaller number x prime and y. Does that make sense to everyone? Okay, I hope so. So we're going to step through a simple example. So here is the fixed point addition definition again. What is plus s of 0, s of s of 0? The first thing we need to do is match on the s constructor. Okay, well, I'm not getting any responses in the chat, so I'll just continue unfolding this definition. So the first thing we do is we match on the s constructor of this leftmost term. So we get s of the sum of 0 and s of 0. Now the next thing we do is evaluate this inner plus. So we have to keep evaluating the function. So we'll match on the 0 constructor, which just returns y, or the second argument to the plus function. So we're going to have s of s of 0, s of s of 0. Then all we need to do is evaluate that to its actual numerical representation. So we have s of 0, which is equal to 3. Now that we have defined these two mathematical objects, one of them being the inductive definition of natural numbers, and the other of them being the fixed point function to represent the concept of addition, we can prove various properties of addition and natural numbers, or addition on natural numbers, using some tactics. So a few tactics that we'll be going over is the simple tactic, which simplifies the terms of your goal by applying function and inductive definitions. Another one is reflexivity, which completes a proof if the left and right-hand side are equal. Another one is rewrite, where if we have some sort of hypothesis, we can rewrite the terms of our goal in terms of our hypothesis. And the last one is going to kind of be a more advanced case where we're going to look at induction. So the simplest theorem that we can do is a specific theorem about some concrete without variables. So let's look at 1 plus 1 equals 2. I'll show you how this looks in the interactive editor in a moment, but overall, we as people know that 1 plus 1 equals 2, but we could also write this simple proof script, which applies the definition of 1 and then shows that 2 is equal to 2. We can also prove more interesting theorems with an existential quantifier. So for instance, this theorem, plus 0x, says that for all natural numbers x, 0 plus x is equal to x. And then again, we write our proof script. So let's try it in the IDE. This is the IDE. So as you can see, I've left in a comment with our inductive definition, our fixed point definition, and our notation to assign to our function. But this is all kind of comes with, it comes built in with COQ. So let's look at the first theorem. So the first theorem is 1 plus 1 is 2. So we've generated in this box here, everything below the line is going to be our goal. And we're going to manipulate our goal using tactics. Everything above the line, and there's nothing right now, but there will be in future examples. Everything above the line is our assumptions, things that we're allowed to assume, things that are in our premises, so to speak. So let's begin our proof script. So we start in our proof script. The first thing that I always do when I write any proofs is I attempt to simplify. So I attempt to rewrite my goal in terms of its definitions. So here's the simple function. Okay, so the simple function rewrote 1 plus 1 in terms of the definition of plus. And what we got was 2. So now our goal is 2 equals 2. The tactic reflexivity is used to solve a proof whenever we have the same thing on the left hand and the right hand side. So because we clearly have that now, we can just apply reflexivity. And now COQ is telling us that we have no more subgoals. So we're finished our proof, and we're allowed to finish our proof script by declaring QED. Okay, done. Let's go on to a slightly more complicated example, plus 0x. So we've got in our goal, for all natural numbers n, 0 plus x equals x. Cool. Let's begin our proof script. So the first thing that we do when we have an existential quantifier like this, for all x, is we can introduce, we can call this tactic called intros x. And what that tactic does is it's the equivalent of, in an informal proof stating, let x be a natural number, or for some natural number x, or statements like that. So let's do that. So now we've moved our x, we've moved our existentially, like our statement about all numbers x into our list of assumptions. So now we say, okay, x is some natural number. That's one of our assumptions. Now we can proceed as usual. We have a goal, and the goal is 0 plus x equals x. Of course, as the first thing we could do is call simple and attempt to apply the definition of plus. So let's do that. Okay, we've called simple. Plus has matched on the 0 constructor and has returned x. Now we've got the same thing on the left and right hand side, and we can call the reflexivity tactic to finish our proof. So now there's no more subgoals. Then we can, since there's no more subgoals, we can complete our proof script by writing QED. Here's a slightly more challenging example. This theorem, plus ID example, says that for all x and y natural numbers, if x equals y, then x plus x equals y plus y. So this is an example of a proof where we have an implication. So if we have x is equal to y, then the statement x plus x equals y plus y must hold. Okay, so let's start our proof script. The first thing we do, again, is to get rid of our existential quantifier by saying, there exists an x and consider some arbitrary x and y. So we intros both of those natural numbers. So we have x, y, natural numbers in our assumptions. Next, we can take our x equals y, that we can take that and we can treat it as a hypothesis. So we can take the statement on the left-hand side of the arrow and take the whole statement and also move it into our assumptions. So let's do that as well. The next thing I'm going to call is intros H. Intros H. Now we have a hypothesis, x equals y. We know that, looking at this, if we just rewrite every single x in terms of y, we would have y plus y equals y plus y, and we could solve our proof. In order to rewrite your goal statement in terms of a hypothesis, we can use this rewrite tactic, rewrite H. So let's do that. Okay, so now we've rewritten our goal in terms of this hypothesis. We have the same thing on the left-hand side and the right-hand side of our equality. So we can finish this proof as well using reflexivity. Okay, and now there's no more subgoals, so we can say QED. There's a slightly more complicated example that I also want to show you, but first I'm going to check if there are any questions. Okay, looks like Neil has answered the question that was there. Thanks, Neil. So let's do a slightly more complicated example, and let's start by doing it informally. So we know that addition is associative. Stated as a theorem, we could say, for any x, y, and z natural numbers, x plus y plus z, where y plus z are in brackets, is equal to x plus y in brackets plus z. And if you are going to be overly pedantic or very detail-oriented and thorough, here's one potential proof that you could do of this statement. Let us proceed by induction on, oh, this is supposed to say x, apologies. Okay, so we'll proceed by induction on x. Let's suppose that x is 0. Then we have to show that 0 plus y plus z is equal to 0 plus y plus z. And we could say that this follows from the definition of plus, because adding plus 0 just returns the same thing. Okay, so that's us proving our base case. Now we can say, suppose that x is the successor of some other number, x prime, where the x prime plus y plus z is equal to x prime plus y plus z. So, we have constructed ourselves an inductive hypothesis. So now we need to show that the successor of x prime plus y plus z is equal to the successor of x prime plus y plus z with the brackets rearranged. And so how do we do that given our inductive hypothesis? Well, we can rearrange the s all the way out to the top level using the definition of plus. So we can say s of something is equal to s of some other thing. And then we could notice that the thing on the left-hand side is equal to the thing on the right-hand side in the inductive hypothesis. So we can rewrite this final statement in terms of our inductive hypothesis, thus proving the statement overall. QED. Okay, so that's kind of the algorithm of how you might do this proof, maybe. And as you can see, it's very possible to write something like this in the COQ proof assistant and show that it's true. Or by virtue of being able to complete this proof, you know that it's true because it's impossible to prove something false inside the logical system that the COQ language implements. Now, just to finish it off, let's step through this in the COQ IDE. All right, so we're trying to prove this theorem plus a COQ. Okay, for all x, y, and z natural numbers, we have x with the brackets around y and z is equal to x plus y plus z. Okay, let's begin our proof script. First thing we want to do, as always, is remove the existential quantifier by introducing a specific case of x, y, and z into our assumptions. So let's do that. Okay, x, y, and z are all natural numbers. We can assume that. Next, we can call induction on x. So if you see in my tactic induction, I have an as statement where I've got some square brackets and some stuff inside the square brackets. That's just some syntactic sugaring that I did to make my example more clear. COQ will assign names to everything automatically, but I just wanted to make the names explicit in this case, so it doesn't functionally change anything. Okay, so let's call induction on x. All right, so what's happened? We now have two goals. The first one, x has been replaced with 0. And in the second one, x has been replaced with s of x prime. So what is this? This, as you can see, as you can probably know already, is the base case is case 1 of 2, and the inductive case is case 2 of 2. So we're going to have to prove both. And as is typical for proofs by induction, we're going to have to prove the base case first. In order to focus in on the first proof, we'll add a bullet point. So that bullet point is this little dashed line here. All right, so now we're focused in on our first proof. This proof is pretty easy. It's identical to two of the proofs that we've just done just now. We can call simple to apply the definition of plus. Now we've got the same thing on the left-hand side and the right-hand side. We can call reflexivity. That proof is complete. All right, so this subproof is complete, but there are some unfocused goals. COQ is prompting you that just because you finished the base case doesn't mean you're done the whole proof overall. You need to focus on the inductive case now. So we'll focus on our second bullet point, which is the inductive case. We have in our assumptions already x prime, y, and z natural numbers. And thankfully, COQ has already given us the correct formation of what our inductive hypothesis is supposed to be. I know when I was taking Math 135 or CO250 or other math courses kind of when I was in first and second year, something I really struggled with was when I was doing proof by induction, I would always write, or not always, but I would often write an incorrect inductive hypothesis. And luckily in COQ, the language just gives you the correct formation of the inductive hypothesis for you. So, no more making that mistake. All right, so let's look at what we have. We have this inductive hypothesis, which states that something is true for a smaller case, and we have to prove it for this larger case. First thing I always do is call simple, attempts to apply definitions. I've called simple, and what has it done? It has taken the S term and moved it outside of the rest of the terms, of the addition terms. And again, it did that because it's applied the definition of plus for one layer. What can we do now? All right, well, as I showed in the informal proof, we have something now in our goal where we can see there's a left-hand side and a right-hand side that looks similar to what we have in our inductive hypothesis. So if we take this, maybe this x prime plus bracket y plus z term and rewrite it in terms of, the inductive hypothesis, we'll have the same thing on the left-hand side and the right-hand side, and we can complete our proof. And that's exactly how we're going to proceed. We're going to call rewrite using the inductive hypothesis, IHX prime. So let's do that. The rewrite proceeded as expected. Now we have the same thing on the left-hand side and the right-hand side. We can call reflexivity. And COQ tells us you have no more sub-goals, which means our proof is complete and we can type QED and finish our proofs. Of course, you can write, if you are willing to define other functions like minus, subtraction, or multiplication, or anything else, you can write all sorts of theorems about your fixed point definitions or about numbers, or there's all sorts of libraries in COQ as well. So you can extend this tool to other courses, beyond just what you can do with natural numbers. And so now going forward, if you were to, before you submit your assignments, do your proof in COQ, you kind of have the most foolproof possible, you have a guarantee to yourself that the logical steps that you took to get from the premise to the conclusion in proving your theorem are correct. And you don't have to wait for a TA to check your proof or anything. And you can see where you went wrong. And this is not something that I had access, I didn't know about this until earlier this year, but this is something you may want to consider in your future courses, learning how to use. So Neil made this meme. If you check your proof in COQ, you stepped on the rake and hit yourself in the face right away. But the TA, it takes a while longer. In order to learn how to use this tool, I read a textbook. I read the textbook, the textbook Logical Foundations, and that's volume 1 in the Software Foundations textbook series. Okay, that's all.
That was so cool. Oh my God.
Yay.
Yeah. All the claps are coming in. Yay.
Clap.
Okay. If you guys have any questions, send them in the Q&A or the chat. How does one clap? I honestly don't know. I think just do the Slack, okay.
Looks like there are some questions in the chat. Okay, so Carrie says, if we want to prove x plus 0 equals 0, left-hand side in the opposite order, will we have to prove x plus y equals y plus x first because plus recurses on the left argument, or is there a simpler way? Okay, so one way, so you're correct in observing that it's important to note that, wait, hold on, x plus 0 does not equal 0. So I'm assuming you mean x plus 0 equals x. So one way to prove this would be to prove that x plus y is equal to y plus x. So basically addition commutes. We couldn't prove it as directly as I had just given a proof because addition recurses on the left argument. You could prove it inductively though, and that's the strategy that kind of the introductory material for this textbook goes in. It proves x plus 0 equals x inductively. But eventually you would prove that x plus y, or addition, is commutative. Okay. Kabir asked, doesn't the definition of plus here implicitly assume associativity, since it's effectively saying 1 plus x plus y equals 1 plus x plus y? Okay, so I think, so, you know, the definition of S, the successor function, it effectively encodes the concept of addition plus 1, but COQ treats it as a separate function. You are right in assuming that by taking the S outside of the argument, we are kind of implicitly assuming associativity. But you should remember that plus is saying something about natural numbers in general, whereas the successor function S kind of implicitly encodes the concept of addition plus 1. So they're actually different things, and we're using these tools to prove something about the general case. So it's valid if we accept our inductive definition of natural numbers. It's valid to still move that S outside the function. Okay, COQ looks really interesting. Is using COQ on homework or on the exam considered cheating? I think so. I'm like not part of the school, but I would say probably don't use it on exams. That sounds like it is cheating. I know that in some offerings of Math 145, they have included COQ at the very end as, like, you know, the final assignment or bonus assignments. I don't. I would just say, yeah, I would agree with Neil. Ask your professors. Yeah. Oh, David Zhao teaches most of Math 145 in COQ. Okay, that's really cool. Yeah, I really like doing proofs in COQ too. Okay, Carrie asks, are there any theoretical loose ends in the soundness of the system? Soundness equal can only prove true things correct. Yes. Or is it more or less fully accepted in industry that COQ proofs are valid real proofs, even for very complex problems? I guess I'll ask Neil to elaborate if my answer isn't sufficient or if he has anything to add. But from what I understand, so COQ is like three things. It is the Galena language, and then it is, on top of that, the LTAC language, which defines tactics which manipulate Galena programs. And then COQ itself is just a type checker. And I think that the Galena language, which we are type checking, is logically, like, it's the logical system that it implements is like sound. And therein is where or why we can only prove, you know, true things. You can only derive valid conclusions from your premises. Carrot asks, is COQ capable of automated theorem proving, i.e. formal verification? Yes, it is. I have like a second and a third talk about that that I have prepared that you can message me for, and I will give you the slides and I will talk you through it if you want. When? Like, it's not planned. I give talks about these topics all the time. There are some advanced tactics. And so there are, there's like, you can program the LTAC language, so you can define tactics in a way where you can automate theorem proving, yeah. Okay, is there any other questions? Yes, Raymond, you could use COQ to prove assignment questions, but your assignment, you'd still have to hand it in like as an informal proof. So you'd still have to practice writing down the actual informal proof and communicating with a human being rather than with a computer. Yeah, you still have to write the COQ program. That's right. But if you write a lot of COQ programs, it gets a lot easier to write them. So Alex says it can take a large amount of time to define everything. And that's true, but there are also many COQ standard libraries that you can use that have all the definitions of things for you. I don't follow academia very closely, but I know that there's lots of papers in which mathematicians, and not like language theorists, but just mathematicians, use the COQ standard libraries to communicate their proofs, because you can give your audience like a script and they can just go run it and verify for themselves whatever your mathematical argument you're trying to make. What is the difference between COQ and SMT solvers like Z3? I don't know. I don't know anything about SMT solvers. I'm an ECE student. I guess Neil, if you want to interrupt and answer, that's cool.
Sure. Yeah. So COQ, you write a proof and it'll verify your proof. SMT solvers, or I guess I'll go stat solvers, but SMT is similar. Is you give an equation like A and B equals B and C and C, and then it'll try to find variables. Try to find A, B, C that will satisfy the truthiness of the whole statement, basically.
Yeah.
So those are more for, you give it a Boolean expression and it tries to satisfy it for you. And yeah, SMTs are a more complicated version of that. So you can have like numbers, for example.
Yeah. Okay. Yeah, and Raymond, as far as I'm concerned, there's no like prove some theorem function. No. If you want to prove something, you can like, you still have to write your own proof script, but within that proof script, there like you can like write things like attempt, like if you're writing a proof script where you end up breaking things down into like many cases, you can automate away the solving of the simpler ones of those cases by saying something like, try this series of tactics, and then maybe you've reduced your problem space from like 20 cases to like 3. Okay, Carrot has a question about SMTs, so I'm going to leave that to MB Terezi. These advanced tactics in which you can find proofs, can they prove a program by themselves for you? No, you can. It's more like you still have to like direct it. It's more like you can reduce, like you can automate away the proving of like some subset of cases when you deconstruct a large problem into many cases. And things like the trivial tactic or the omega tactic or the Leah tactic, those depend on like your goal statement being in some closed like logical system. Like I think the textbook I was reading briefly mentioned Pressburger logic. And if like, the goal statement that you have and some collection of your hypothesis like fit into like whatever Pressburger logic is, calling omega or Leah on that statement will just auto solve it for you. But I think this, like the prerequisite for this is that your goal and your hypotheses have to be constrained within some like first order logical system. Otherwise, you're going to have to solve it. Like you're going to have to manipulate the program using tactics yourself.